The transformer architecture revolutionizes processing sequences by employing layers that learn context through self-attention. It effectively captures relationships between words regardless of their positions, resulting in parallelizable operations that outperform prior sequential models. Designed to tackle tasks such as translation and text generation, its impact is widespread across various NLP applications. Multi-head attention enhances learning by enabling models to focus on different parts of input data simultaneously. By incorporating multiple attention mechanisms, it captures diverse aspects of information across the sequence, leading to a more complete understanding of the input. This parallel attention structure allows for efficient handling of complex language patterns. Self-attention facilitates context-aware processing by considering the entire input sequence when determining relevance. This method allows for the dynamic weighting of each word in relation to the others, creating internal contextual representations. It not only handles inputs of variable lengths, but also reduces the impact of sentence position on understanding. The scaled dot product is a critical mathematical operation within self-attention that calculates the attention scores between words. By scaling these dot products, it stabilizes gradients, ensuring the effective training of deep networks. This calculation is essential for identifying how strongly words within a sequence are associated with each other. Attention weights quantify the importance of different words in the sequence to enhance context relevance. They adjust dynamically, affecting which elements of the input receive more focus during processing. These weights ensure that the model emphasizes significant words while keeping less crucial data in the background. The Softmax function is instrumental in normalizing scores within self-attention, transforming arbitrary values into probability distributions. By converting numerical scores into probabilities, it ensures that they sum to 1, facilitating effective comparisons. This enables the attention mechanism to focus on the most relevant parts of the input. Input embedding is designed to transform input data by converting each instance of data into a fixed-size vector, effectively capturing its semantic essence. This procedure facilitates efficient processing and superbly prepares data for subsequent layers. Through dimensional reduction, it optimizes computational complexity while preserving meaningful context. Positional encoding integrates sequence information into embeddings, effectively enabling the network to comprehend the order of words or data points. This technique imparts a spatial context to embeddings, which is crucial for tasks requiring sequential understanding. By representing positions through trigonometric functions, it allows models to retain order without learning it explicitly. By representing words as token embeddings, each word is transformed into a high-dimensional vector, capturing its semantic nuances. This method facilitates the model to recognize and differentiate words within context, effectively enhancing understanding. Through embeddings, words are contextualized, making semantic relationships more discernible. Output processing within multi-head attention generates predictions by further refining computed attention values into digestible formats. Utilizing these refined outputs, it translates them into actionable insights, leading to accurate predictions. This processing step ensures that the model output aligns closely with intended applications, enhancing utility. Linear transformation modifies vector spaces by adjusting dimensions to fit the architecture's needs and specifications. It primarily serves to transform data outputs to align dimensions correctly with the subsequent processes. This transformation ensures that the multi-head attention mechanism operates efficiently and effectively on consistent input shapes. Softmax layer converts raw scores into a probability distribution, providing insights on relative likelihoods of each class. It achieves this by normalizing outputs such that they sum to unity, due to the exponential activation function. This adjustment process helps in translating fixed-dimension outputs into interpretable probabilities for decision-making. Layer normalization applies normalization to reduce internal covariate shifts, thereby stabilizing learning. It normalizes across the features independently for each input, preserving the core signal integrity. This steadying process is critical for increasing the model's robustness and mitigating training fluctuations. Normalization layer enhances model performance by balancing outputs within each layer. It aligns statistics of activation functions to ensure they behave predictably under varying inputs. This balance prevents unstable gradients and helps maintain consistent data flow through different network layers. Residual connections ensure information coherence by allowing direct pathways for gradients. They combat issues like vanishing gradients by adding bypasses for direct data propagation without degradation. This strategy maintains a stable gradient flow, facilitating efficient model training and effective learning. The encoder block efficiently manages input data through parallel layers, transforming raw data into structured information. It receives inputs, applying complex transformations to generate context-aware representations. By leveraging advanced techniques, it enhances the transformer's capability to understand intricate patterns. In the encoder layers, inputs pass through multiple layers designed to progressively refine and abstract data features. These layers work together, constantly updating configurations to realize high-level transformations. Their collective operation results in the continuous refining of data for clearer insights. Attention heads provide multiple perspectives by focusing on different parts of the input simultaneously, allowing for a rich analysis of textual data. They excel at capturing contextual information, which is crucial for understanding nuances in data. Each head evaluates distinct data aspects, leading to a diverse range of interpretations. The feed-forward component processes the output from attention layers, fine-tuning representations before advancing them along the network. It introduces nonlinearity and complexity, enhancing the model's ability to capture subtle patterns. This section operates independently, ensuring every data piece is thoroughly processed. Adds and norm performs a vital layer setup function by normalizing outputs while allowing the model to retain important signals. Through residual connections, it ensures stability in training and avoids vanishing gradients. This mechanism optimizes interlayer communication, promoting efficient data flow throughout. The decoder block is integral to the transformer architecture, crafted to process outputs through a series of structured operations. It comprises layers dedicated to refining and optimizing data for further decision-making. This mechanism ensures that intricate input details are not lost during the decoding process. Located within the decoder block, decoder layers are tasked with handling the complex predictions necessary for effective translation of encoded information. These layers integrate several components, each contributing to the accuracy and fluency of the outputs. By layering, they improve tasks like language modeling and sequence generation. The attention mechanism in decoder layers is pivotal for ensuring the model attends to encoder outputs effectively, forming a bridge between encoded inputs and potential predictions. Its structure allows it to determine relevance by drawing focus upon crucial input segments. This capability helps the model prioritize essential information over irrelevant data. Mass detention is a specialized strategy within the decoder layers that imposes a causal structure on the output generation process. By restricting visibility to future positions during training, this mechanism establishes sequential dependencies, requiring outputs to be generated based only on preceding inputs. This approach is key to maintaining logical coherence in tasks like sequential prediction. The feed-forward component in decoder layers performs transformation operations that model the complex, nonlinear relationships within data. Working independently per position, these layers are optimized for speed and efficiency, applying learned weights to enhance feature extraction. This component complements the attention processes by adding additional depth to the model's predictive capabilities. Adds and norm is an integral component for stabilizing the transformer decoder layers through additive normalization. It applies normalization to the sum of its inputs, enhancing model stability and convergence. This layer configuration ensures the consistency of inputs, mitigating issues from residual connections. Model integration harmonizes the interplay of the encoder and decoder within the transformer architecture. It ensures alignment of information flow between these components, thereby facilitating efficient data processing. By optimizing interactions, it bolsters the model's capability to manage complex data networks. Sequential processing orchestrates the movement of data through various layers, adapting to the architecture's need to handle sequences. This mechanism ensures orderly data transformation, maintaining the sequence integrity as information progresses. By structuring data, it supports the architecture's ability to process sequential inputs effectively. Encoder-Decoder attention acts as a bridge between two blocks, facilitating communication and interaction. This attention mechanism evaluates and maps encoded details onto the decoder, enhancing contextual relevance in predictions. By linking layers, it improves the ability to generate coherent outputs while processing sequences. Final outputs emanate directly from the integration of model components, producing comprehensive results. This stage converts processed data from earlier layers into the model's predictions, culminating the entire model's efforts. With a focus on accuracy, these outputs reflect integrations and learning achieved across sequences. The summation and norm aspect focuses on aggregating outputs to derive meaningful final results. It plays an essential role in combining different steps to ensure coherent results. Through accurate collation, it contributes significantly to model integration processes. The training process involves systematically updating model parameters to enhance learning efficiency. It operates within the transformer architecture, utilizing data-driven approaches for improvements. The process ensures that models are continuously optimized for accurate predictions.